I'm not right. I'm just writing the problems right now. So the problem is max px xy subject to. I know you're not seeing the screen, but trust me, you're not really missing much. Okay. Write down Lagrangian critical point sign constraint. Okay, cool. All right, so I just wrote the problems now, and we're just going to write the Lagrangian to start with. So point A, we're going to write the Lagrangian down and solve it and do et cetera, et cetera. So setting up the Lagrangian, it's pretty standard. The function I need to maximize, so minus px minus qi minus a lambda xy minus a. Okay, standard, nothing special with the Lagrangian. Now, how do we solve this? You take the derivatives with respect to x. I've seen people write this, I'm fine with it. I've seen people write this, I'm fine with it. Everything is fine. Okay, as long as I clearly understand what you're doing. So I take derivative with respect to x of this function, and I get minus p minus lambda x is equal to 0. And then L, I look to write it like this, so I'm going to stick to this, but again, there's nothing wrong with your choice. So I think I messed it up. This is an x, and this is a y. I guess it's too early in the morning even for my derivative. Okay. And for the Lagrangian, it is personal taste. I would say I would even push it further, but I'm not seeing it emphasized that much in this class. But what I also do in the Lagrangian is I also write derivative with respect to lambda. Okay. So I just get x, y minus a is equal to 0. You might ask, why am I doing this? The reason is that I'm just getting the constraint, which is true. But the reason I'm always writing this is because now I more or less have all the equations I'm going to need to solve this problem right here. I don't need to look here and then remember to look there and et cetera, et cetera. I have all the equations I need here, and I know that based off these three, I'm going to solve the problem. I don't know how. Some cases might be more complicated, obviously, but with these three, with derivative with respect to x, derivative with respect to y, and derivative with respect to lambda, in a Lagrangian case, I'm going to solve the problem. Okay, that's why I like to keep them together. Yeah. Okay. Cool. So let's see. From the first, let's put it 1, 2, 3. From 1, I get p minus p is equal to minus lambda y. It's actually a plus, right? Actually plus lambda y. Okay, so y is, so one way to think about it, the way I like to do it is just put lambda on one side and everything dy on the other side. There's another, you can just express y in terms of lambda and then replace it in the last condition. There's no particular case in which you have to do it, okay? But the way I'll do it is I'm just going to write it as lambda. I get minus p over y. Similarly, from 2, I have minus q is equal to lambda x. So I get lambda is equal to minus q over x. And then the main observation is that lambda is the same everywhere. So I get p over y is equal to q over x. So I can just write it from here that, I don't know, x is equal to p over q y. Does that look right? Yeah. Yeah, it's Q over P. Yeah, I was looking at it. Telling you guys, 8 a.m. is too early to do math. Let me do my notes here. It's Q over P. That is correct. All right. Cool. And now what I do with this is I just take this relationship, plug it into here, and I'm going to get X and Y. So I'm going to get Q over P times Y minus A is equal to 0, which is Q over P. Y squared is equal to A. So it means that Y is just equal to square root of A, P, Q. Okay? Now, one short check that I want to make is the fact that Y is positive. Otherwise, I might have plus minus here. I don't know. So I'm just going to check where Y is positive. They don't really specify the Y is positive. So my correct full answer would be plus minus, because I don't know. Plus minus. But I think me and Adam agreed partially that we're only going to look at the plus solution for this, because it doesn't really make sense to buy, you know, if you're looking for an economic context, it doesn't really make sense for the quantities to be negative. So I think we're just going to stick with the positive one. But again, really careful here. Okay. You need to show me that you thought of the fact that, you know, it's a plus and a minus. If you only take the plus in this case, and I might understand, but I need to see that it is not an oversight. It is that you actually thought about it and you decided a conscious decision to take the plus. Okay. Anyway, now my X is just going to be Q times P times square root of APQ. And I've actually seen a lot of people having trouble with multiplication outside of the square root. So, and the way I would, if you can't see it really fast, the way I would advise you to deal with it is just write whatever is outside, put it under the root square root first. So what I mean by this is, if this is outside, it means that it is squared underneath the square root. Make sense? Pretty basic, right? But when you're doing it really fast, you might just simplify stuff and mess it up. So you get this, and now you have A, P over Q times Q squared times P squared, everything under the square root. This simplifies with this simplifies with this. So A, Q, P. Okay? Everyone fine? More or less what I did? And now I'm going to claim these are my solutions. This is one, this is the other. Again, I consider the plus ones, but you have to know that the minus one applies as well. Okay, any questions on this, or should I go point B? Cool, point B. I think I can do it, yeah. Okay. Point B. Point B asks me, the side constraint satisfied strict inequality. What do you know about the multiplier in this case? This should have became more or less mechanically already for you guys. In the sense that when you see the constraint being strict, so XY is smaller than A, which actually is the right, is it the right form? No, this was a mistake in the notes. We corrected it in all the workshops. Your initial constraint was minus XY, smaller or equal to minus A. And what the professor obviously meant to say was minus XY strictly smaller than minus A, obviously. Okay? It was just an oversight on his behalf. He missed the minuses. Happens to the best of us. And no, that is not a free pass that you can miss minuses on the exam. Happens only to the professor. Okay. So you have this. you automatically should think what the conductor says in this case, which is if it's strict, lambda has to be 0. Okay? Now, what do I do with this lambda 0? Big mistake. Do not do this. Do not plug your lambda here. No. Big no. Okay? Do not plug your lambda in the objective function, L. Okay? Remember, this L has to be true. This function has to be defined for all values of lambda and all values of x and y. So do not plug your values here. Okay? Do not plug them in the objective functions. I'm even gonna write. Because I've seen a lot of people and then they ask me, well, this doesn't make sense anymore. Well, yeah, because mathematically you're ruining the structure by plugging this lambda 0. So do not plug in the Lagrangian. Okay? Do not plug it in there. What can you do with it? Plug it in derivatives or first order. However you want to call it. Okay? So you plug these values in the derivative. You do not plug them in the objective function. Because if you plug them in the objective function, you might get nonsense. So do not do that. Okay? Moving on. If you look at my conditions that I got from the derivative, which is lambda is equal to minus py and lambda is equal to minus qx. Lambda is equal to minus py, which is equal to minus qx. Remember, these I got from the derivatives, okay? If I got it from the derivatives, it means I can replace here with 0. So I get 0 is equal to minus p over q, p over y. Okay, is equal to minus q over x. Automatically means p and q is 0. And now this is this is really bad under a lot of circumstances. First of all, the problem gives you p and q being some constants, and you tell them that it's 0. So this is not okay to start with. And then remember, we had to maximize minus px, I think it was. Yeah, minus px minus qy over x and y. And if you just replace them here, you get to maximize minus 0 over xy. So you're maximizing a constant over some variables, question mark. What's the point of this? Makes sense? You can't maximize a constant. A constant has a value given. So this problem, this doesn't make sense. Makes sense. Again, why? Because if I just replace them, I have to maximize a constant over x and y. So basically, whatever value of x and y is good, because I'm still gonna have the same value. It doesn't make sense. I don't want to get into nonsense. Okay, doesn't make sense. So now coming back to the question of the problem was, what can you say about the multiplier lambda? I said a lot about it. I said it's 0. And then can I exclude this case? Yes, because the problem doesn't make sense. So the yes, I can exclude it because this problem doesn't make sense. Any questions on this? So again, really big mistake is after you apply Contactor, do not replace the lambda in the objective function. You can replace them in the derivative, not in the objective function. Okay. No questions here means we can go. Yeah, we can go to point C, I guess. Expenditure function, etc. Okay. So then he gives us this more complicated stuff, which is E of P. Is that a bar? No, it's not. P, Q, U bar. And I have to minimize P of X, X and Y, plus QY subject to XY greater or equal to U bar. Sure. Okay. So now I think I know. I think I know how to do this, maybe. Okay. So I'm given this expenditure function, right? And now they're asking me, why do I know the solution to this thing? Okay. If you look for your notes, I don't know, on a page or something, for me, it would be too much to scroll back. Previously I had to maximize minus PX minus QY. Now, my claim is that this as value and everything basically is going to be the minimum equal to minimum of PX plus QY. Why? Okay, why is this? Well, just think about it for a second. If I have a minus A, okay, and I want to maximize this. If I want to maximize minus A, do I want A to be small or big? If I want to maximize minus A. Do I want minus 1 million or minus 1? I want minus 1, okay, obviously, because I want to maximize the value of minus A. So my claim is when I want to maximize the minus A, I just want to find the smallest A. So it's just minimum of A. Make sense? Yeah. Okay, cool. So now we agreed on the fact that this is the same. Okay? That instead of maximizing something negative, it's the same as minimizing the positive thing. Okay? We agree on this. Now let's look at the constraint. My initial constraint was minus xy small or equal to minus A. Now this constraint is xy greater or equal to U bar. Yeah, it's just a minus, right? This is if I just same with A is equal to U bar. Okay, obviously I just multiply it by minus 1. Okay, now comes the I guess the trickier part, I guess, a little bit, in the sense that we have shown, so really important, we have shown that the Contactor problem from A is the same as the problem from C. Okay, you guys agree? This is what we've shown up to this point. We have shown that this problem up top with the minimizing is the same as the problem with maximizing. Okay, the Contactor one. So what do I mean? Let me show you on here. I hope I've convinced you that this problem over here is the same as this problem over here. Okay? This is what I wanted to show you for now. But now comes the more interesting question, in my opinion, which is like the heart of the, I would assume, Contactor and Lagrangian method, if you want to call it, is the solution to this, I don't know, the pair XY, the same as the solution to this? Remember, we have solved the Lagrangian. We have solved the Lagrangian case, this one would equal. I have not solved per se this one, okay? So now the whole idea is, how can I use the solution from the Lagrangian in the solution and, you know, maybe get the solution for the Contactor? Does my question make sense to you guys? Like what I'm trying to show you. So I have shown that the solution to this is the same as the solution to the Contactor. But now, why is the solution to the Contactor the same as the solution to the Lagrangian? Make sense? Look what I'm asking you, guys. Okay. And this is where the two cases of the Contactor, the complementary slackness condition, I think it's called. I'm really bad with names. I never memorized them. So this is where the whole Contactor, conditions come into play. What are the Contactor conditions telling you? the complementary slackness. Okay, we're gonna have a conversation about what does it mean to have the whole condition of contactors. But the complementary slackness basically says like this. It says that if I have minus xy strictly smaller than minus a, then I have lambda is equal to 0. And then I have that if minus xy is equal to minus a, then lambda is greater or equal to 0. Fair? These are the complementary slackness. You could have copied them off the books, up there, whatever. I didn't do anything to them. Okay? So these two cases, case 1 and case 2, basically, if you combine them, you get the condition minus xy smaller or equal to a. Right? Like if it's smaller or equal, then it means it's either equal or small, strictly smaller. So these are the two cases that are making this, this restriction. Now, what is this case? What is this case? When the constraint is equal, what is this case? It is just the Lagrangian, right? Like let's look again at the problem. What's just the right mouse? Okay. Let's look again at the problem. The only difference between the contactor and the Lagrangian is the fact that here I have small or equal and here I have equal. So in the case where this is binding, where it's equal, the contactor just becomes the Lagrangian problem. Does that make sense? Does that claim make sense to you guys? Look at, I'm not inventing stuff, I swear. I basically just said here, in the second case, where it's binding, where the constraint is equal, I'm gonna have lambda is greater or equal to 0, true, but my claim is that this is just the Lagrangian case. Okay? And now comes in point B, I think. Yeah, point B here. We have shown in point B that the first case has no solution. Remember the whole discussion where I'm maximizing over 0, so there's no point in looking in there. Okay? So I'll try to write really small here. No solution. No nonsense, if you want. Okay. Cool. So my whole inequality is split into these two cases. Where in the first case, I have no solution, and in the second case, I have a solution. So it means that the solution to this whole thing, the combination of them, is just the solution from the Lagrangian. Why? Because there's no solution in the other case. Make sense? When I'm looking for a solution to my problem, to this problem, I'm either looking for a solution in the case where it's equal, or I'm looking for a solution in the case where it's strictly smaller. In the case that it's strictly smaller, you guys have shown in point B that there's absolutely no solution. So it means that if it is a solution, it's just a solution from the Lagrangian. Okay? So wrapping it back up, if you want like the big, the big brain logic, I have that this E, P, Q, U bar, whatever, which is PX plus QI, what was it, XY smaller equal to U bar. Okay, I said that, I have to minimize this. So the first argument, the first logic is this problem same as KT problem, okay? Then the logic is split KT into, I'm going to write in quotes here because this is the phrasing and everything I'm saying here is more or less for you guys to understand what's going on. You don't need to write in the paper, I'm splitting K2 into the two cases, okay? You're just writing the complementary slackness condition. So split KT using the complementary slackness conditions. I'll just put parentheses into the Lagrangian and strict case. And then the logic is Lagrangian has a solution. Strict case, no solution. Which means, not Lambda, which means KT has a solution. And which is the solution? It's definitely not the strict case. So it's the Lagrangian. Has a solution, same as Lagrangian. Okay? Does everyone understand the train of thought that I used here? This is like the same logic you're going to apply in 99.9% of the problems. Okay? You can solve the Lagrangian, and then you split the KT into the case where lambda is equal to 0 and the Lagrangian case which you already solved. And then you see what's happening afterwards. Okay? So now this is the big brain roadmap why I know the solution to this min of A whatever, etc. It's the same solution as the Lagrangian. Okay, cool. Any questions here? Okay. Now for point D, they're asking us compute the expenditure function using the results from A and B. So expenditure P, Q, and U bar is again PX plus QI. And compute the expenditure function is just a fancy term for replace X and Y with their Lagrangian values. So I hope I'm not wrong, but this was square root of, I had A here, but I'm not going to use A anymore. I'm just going to use U bar, okay, instead of A. U bar QP, that's about right. And then this is U bar PQ, okay? And I'm just going to take these and plug them here. So I'm going to get E of PQ and U bar as being, again, P times square root of U bar QP plus Q times U bar PQ. And again, I'm going to write it straight out, but if you're not really okay with multiplying square roots, just take it slow. This P is just square root of P squared, and you multiply them nicely, and you just get square root of U bar QP plus square root of U bar PQ. So you just get 2 square root of U bar PQ. Okay. This was actually pretty easy. What's the time? That's good. Okay, and now for E. For E, it's just asking me to compute the derivative of E with respect to P. So I'm just going to take a derivative with respect to U bar PQ with respect to P. So this is just, again, you can write it a little bit nicer, square root of P times square root of U bar Q. And this is just 2 times a half, P to the power of minus a half, square root of U bar Q, half. So this is just square root of U bar Q over P. Okay. Yeah, and now we're just going to take like a 10-minute break, and then we're going to do the next problem from this thing, and maybe problem number 2 from one of the Stumble groups. Why I want to do that is because that is one of the only problems I've seen that actually has a solution in the strict case of the contactor, okay? It's important to not take as granted that always the strict case is not going to have a solution, okay? In some cases, it might. This is just in this case that the strict case does not have a solution. And we're going to see in the next, that problem, that the contactor actually has a solution in the strict case, okay? So yeah, let's take a 10-minute break right now, and we'll pick it up from there. Yeah. I think this is the last one. Okay, guys. I think 10 minutes passed, so let's get back to it. So we're gonna do problem 83, which as opposed to what you may think, it's actually pretty fast if you know some stuff. And I know stuff because I'm lazy. It's not really a good thing. But yeah, I'm gonna show you something really fast. So a cool trick here. And I kind of showed it to some of you, and now I want to share it with all of you. Yeah, there's not much else. I don't know where I was going for. Wait a minute. Cool. So yeah, let's the first problem. This is the problem. It just gives us maximize the U with a constraint. The U looks like this, a sum of natural logs, and then you get some fancy stuff here, which you're going to dive into. But this is the utmost standard Lagrangian problem that you can get. The phrasing is just, yeah, completely standard. So let's just solve it completely standard. We create our Lagrangian, which is just U of x1, x2, x3 minus lambda p1 x1 plus p2 x2 plus p3 x3 minus m. Okay, and now you just take derivatives. Derivative with respect to x1, and you get. At this point, I'm just gonna, since the emphasis is not on the derivatives anymore, I'm just gonna take them. You know, here derivative is gonna be 1 over x1 minus 6 minus lambda p1. Yep. Is equal to 0. Derivative with respect to x2 is just 1 over x2 minus 5 minus lambda to p2 is equal to 0. And derivative with respect to x3 is equal to 1 minus x3 minus 4. Math is hard. Okay. No lambdas here, no numbers here. P3 is equal to 0. And then for the last condition, I am going to write my own. I think in some classes it's required. I think in Sweden it's required. I think it's in the West is required, but I don't know about Norway. I find stuff new every day. So if you take the derivative of lambda, you just get a constraint. I'll recommend writing it, especially if you want to have a go. You know, if you're ever going to write this in a more international approach, you are expected to write the derivative with respect to lambda. Okay. Now let's see what we get. Again, my strat in solving most of them is just using the fact that lambda is equal everywhere. So that's kind of my idea of how I solve problems. Is it the best and fastest way? Not really. Sometimes it depends, right? It depends on the system of equations. In this case, I would assume it is, but I might be wrong. Lambda is just going to be equal to 1 x1 minus 6 times p1. Lambda is equal to 1 over x2 minus 5 p2. And lambda is equal to 1 over x3 minus 4 p3.
You're missing a 2.
I'm missing a 2. Oh. So you're saying I just copied it wrong. I didn't write the derivative wrong. I don't know which one is worse, to be honest. But yes, he's right. There's a 2 here. Right here. So it means there's a 2 here. So it means there's a 2 here. No biggie, but still, my results would have been completely different. Okay, so I wrote these things. And what I said is that I'm going to take advantage of the fact that the lambda is equal everywhere. Okay, that is what I'm going to take advantage of. So I'm going to have lambda is equal to 1, x1 minus 6, p1 is equal to 2, x2 minus 5, p2 is equal to 1, x3 minus 4, p3. Okay, Disclaimer. What you have learned in this class and what you should learn in this class and what you should do most of the cases in this class is just express x1 in terms of lambda, x2 in terms of lambda, x3 in terms of lambda, and then replace it all here and compute it. Now, how fast is that? I think I could do it in 5 to 10 minutes, but I don't think many of you would follow. I think on the average person, it would take 20 to 30 minutes. So that would take a while, but it is the standard approach to take in these cases because you will 100% get a result at some point, okay? Now, since I'm here, I'm more or less doing the plenary session, so I'm solving it for you, kinda. I thought it would be a waste not show you some cool thing. So I'm gonna show you the cool thing, but I am gonna, again, even I told you in speech, but I'm gonna write by myself. The standard approach is to just express something in terms of the other and plug it in to the last condition, and you're gonna solve it, okay? So that is the complete standard approach. In this case, it would just be standard approach, which should work in 99% of the cases. It might just be a little bit workaholic, but the standard approach is, I don't know, you can, I guess, express x1, x2, x3 in terms of lambda, replace x1, x2, x3 in DL lambda / budget constraint. And we're gonna do estimated time of work. I think if you get this to be done in less than 10 minutes, you should be fine, okay? This is my approximation of how fast you should do this computation. Now, this is really, it's just worky, but it's gonna give you the answer. I just wanna show you something cool, okay? I don't know how, I've been surprised that not a lot of you know this property right here. If you have two fractions, A over B is equal to C over D, then this is also equal to A plus C over B plus D, okay? So I'm just gonna take advantage. The proof for this is like extremely simple. But I'm not gonna do it. There's no need to. But it's like one line. I think I showed it to some of you guys. Anyway, so I'm just gonna use this property. I'm gonna just use it here. Okay. Again, this is just because I'm lazy and I know stuff. The standard approach: express everything in terms of lambda or etc. Replace them in the budget constraint. Solve it. Okay, that is absolute standard approach. Will always give you a solution. This thing that I just showed you right now, in 99% of the cases, it's not going to give you a solution. It just happens to work this time. Okay. So I just want to show you like how cool it is, how fast it is. So it means that my lambda, which is equal to 1 x1 minus 6 c1, is equal to 2 x2 minus 5 p2 is equal to 1 x3 minus 4 p3 is equal to, let's see, what is it equal to? Is equal to, let's use the formula, okay? It's equal to, I just add the denominator, so I have 1 plus 2 plus 1, and underneath I just add them again. X minus 1 minus 6 p1 plus x2 minus 5 p2 plus x3 minus 4 p3. There's an equal sign here, so I'm not adding the fraction. It's standard, just equal, equal, equal. Okay? Cool. Why is this writing so extremely helpful? Well, let's look on the other page. I'm still using the equal sign, okay? No plus, no minus is still equal. So up top, I have 2, 1 plus 2 plus 1, that's 4. And now I'm just gonna open the parentheses here. So I'm gonna get x1 P1 minus 6 P1 plus x2 P2 minus 5 P2 plus x3 P3 minus 4 P3. Okay, I just opened the parentheses there. Okay, and now you might say, okay, fair, you did this fancy trick, but we didn't get anywhere. We still have x's here, so we're not gonna be able to solve it. Fair, almost. I have x1 P1 plus x2 P2 plus x3 P3. This is equal to m, right? It's from your budget constraint or whatever. So this is just equal to 4 n minus 6 P1 minus 5 P2 minus 4 P3. Okay? So this is what I mean that I got the answer really fast, because now remember, I only use equal sign. No adding, no multiplying, only equal signs. So my lambda is equal to that thing, which looks really nice. But in particular, also these fractions are equal to that. So this is equal to lambda. It's good. It's always good to find out lambda. Then then the fractions 1 x1 minus 6 P1 is equal to this. Okay. And now we just do this, multiply like this, and you get 4 x1 minus 6 P1 is equal to n minus 6 P1 minus 5 P2 minus 4 P3. And after some very simple calculus, you get x1 is equal to n minus 6 P1 minus 5 P2 minus 4 P3, 4 P1 plus 6, which is just equal to x1. You know, this 6 is just 24 P1 over 4 P1. So I just get m plus 18 P1, 5 P2, 4 P3, 4 P1. Okay? There's nothing really, I guess after I get this, everything else is like, it's just like the simplest math you can get. I know it might look more complicated than it is. That's the unfortunate thing of following somebody else's notes. I think I've tried following some of you guys' calculus or whatever. And although it was the simplest calculus, I still could not. So maybe sometimes it's good to just take some time, let it sink in, and maybe, scratch it for yourself at some point. But I'm telling you, after this, it's really easy. Anyway, so I got my x1. One observation: whenever the problem says solve the problem or solve the solution, solve the Lagrangian, they are not asking for lambda. They are asking for this. Okay, they are asking for x1, x2, and x3. If you ever have doubts, think of it this way. Somebody comes and asks you, which stocks should I invest in? Should I invest in Google, Apple, or Tesla? How should I invest in them, right? And then you think for a second and you're like, yeah, your lambda is 2.175. What does that even tell the person about the stocks? Nothing, right? You want to tell them you buy 2 stocks of Apple, 2 stocks of Tesla, and 1 of Google, okay? These are your x1s. You want to get x1 is equal to something that I can compute, x2 is equal to something, and x3 is equal to something. So right now, I'm just going to compute x2 as well. So I get x2 minus 5p2 what was it? Sorry about that. Is equal to, again, 4m minus 6p1 minus 5p2 minus 4p3. By the way, the investment on Tesla and everything, that is not a serious investment advice, by the way. So do not take it as it is. Yeah. What I'm doing right now is I'm just making all the fractions before equal to my newly computed fraction, and I'm computing x2 and x3 out. There's nothing, if I were you, could just let me do the work, because realistically, you've seen where I posted the notes, right? I think I made a new folder online. So you have these notes, and it's more valuable to just follow the procedure, what I'm doing, rather than the math behind it. Yes, it should be 2. Thank you. I'm so familiar with this. Yes, there's a 2 here. See, that's actually good that you're following my notes. Thank you. Okay, there's a 2 there. Yeah. Okay. 2 here. 4p2 plus 5. I simplify here by 2. 2. So I get x2 is equal to, this is 10p2 over 2. So I just get m minus 6p1 plus 5p2 minus 4p3 over 2p2. And for x3, I would just try to guess it in computer mentally, just because I think there's a waste of time. There's a waste in basically just making a fraction equal to whatever again, et cetera, et cetera. So I think the value is going to be 4p3 plus 416 m minus 6p1 minus 5p2 plus I think it's going to be 12p3. Might be wrong, but people that did this, I hope it's right. Should be right. Okay, so these are my answers. When you're asked to solve a problem, you can even square your answer, like x1, x2, x3. This is what it means to solve the problem. Okay, you're not done until you have shown me x1, x2, and x3. Express that as something that I can actually solve. Like I can solve it. Okay, if they would give me m, p1, p2, p3, which they would if they wanted me to give them numerical solutions, then I could solve it. I'll just plug in the numbers here and I'll tell them x2 is equal to 5. Okay? Okay, now point B. Point B is was asking, let's skip the page actually. Point B was asking us to compute U star and then the derivative. U star of P1, P2, P3, N is just a fancy term for replacing, writing my function. Yeah. Okay. It's just a fancy term for replacing my function. So it would be X star, which depends, as you saw, on P1, P2, P3, and N, minus 6 plus 2 log of X2 star, my solution basically. P1, P2, P3, N. You don't need to write it this way. I'm more or less writing it this way to explain to you why this U star depends on P1, P2, P3, Pm. It is because my solutions to the previous problem depend on P1, P2, P3, and N. Okay? So if I plug in these values, if I plug my X1 here, X2 here, and my X3 here, then the function is not going to depend on X1, X2 anymore. It's going to depend on P1, P2, P3, N. Okay? Because X1 and X2 and X3 depend on P1, P2, P3, N. So what I mean by this is I'm just going to replace our problems. Yeah. Let's see. This is ln of X1 star was something like n plus 18p1 minus 5p2 minus 4p3 over 4p1 minus 6. And this is just going to give me, this is just going to give me log of m minus 6 minus 6p1 minus 5p2 minus, oh, sorry, I have to, this is just this one, so it would be plus the others. I was just computing this one. Let me see what we can do here. Okay, so it will be plus, this is x1 plus log of m. This is over 2p2. What was it here? It was 6p1 plus 5p2 minus 4p3 minus 5 plus, and now my last one, my x3, m minus 6p1 minus 5p2 plus 12p3 over 4p3 minus 4. And I'm just gonna write everything straightforward. I don't want to replace everything, etc. I think this, if you just do the math inside here, the 6, we can write it 24p1 over 4p1. This is 10p2 over 2p2. And this is 16p3 over 4p3. And my claim is that you are going to get ln of m minus 6p1 minus 5p2 minus 4p3, 4p1 plus log of m minus 6p1 minus 5p2 minus 4p3 over 2p2 plus log of m minus 6p1 minus 5p2 minus 4p3 over 4p3. Why can I do it relatively fast? Because I know it's symmetric, but that's something that will come through practice with computation. So now what we're going to use here is the log rule. The log rule that I'm going to use here is, two of them. Log of a over b is log of a minus log of b, natural log. And then log of ab is equal to log of a plus log of b. Okay, they're the standard log procedure. So I'm going to use it for the fraction here. And I'm going to get, for this fraction, for the first one, I'm going to get, if I can switch the page, I'm going to get something. Yeah. I'm going to get log of m minus 6p1 minus 5p2 minus 4p3 minus, and then I had log of 6 with log of 4 plus log of p1, okay, plus log of the same thing minus log of 2 plus log of p2. Also, I can't see, sorry for that. Plus log of the same thing up top minus log of 4 plus log of p2. Okay, cool. So this is just shorthand for 3 log of this monster over here minus 2 plus 2, 4, minus log of 2 minus log of p1, p2, p3. I just wrote it as a product. Okay, so this is my answer. Again, everything I did here is I just replaced and did some math. Okay, again, it's good practice because I think being adept at computing stuff is going to help. Especially in the exam, because in the exam sometimes on some problems you might not know what the exact solution is from start, which happens to the best of us. So at that point, you're just going to try stuff. Okay, you're going to see if something works. Now, if you can try something in 10 minutes, then it's perfect, right? Because you only know in this class like 3 methods in total. So in 30 minutes, you're going to solve a problem. But if one try, because you're computing really slow, takes you half an hour, then you might run into a time crunch really, really fast. Okay? Like all the good mathematicians are not really, okay, some of them are really brilliant. They see the solution right off the bat, but that's like 0.01%. The vast majority just try different methods and are really good at computing stuff. Okay? Awesome. So I got this, and now I got to compute my du star with respect to m. So I have to take a derivative of all this thing with respect to m. And now, where do I see m? Only here. That's the only place I see m. P1, P2, P3 does not depend on m. 4 and log of 2 does not depend on m. So when I take derivative, I just take the derivative of this log, and I get 3 times 1 m minus 6p1 minus 5p2 minus 4p3. Okay, that is fine. Times 1. Yeah, I forgot a 2 again. Yes, I was looking at that. Let's see if you're good at math and computation, unlike me, where you get a 2 here. Yeah, it's gonna work out nice. Wait, 1 second. Okay. Okay. Yeah, I forgot a fucking 2 here. Okay, cool. So it's gonna be 4 here. After some easier math, I'm just gonna add 2 of that, of course. I was gonna have 4 here, 4 times this thing, which is gonna be equal to lambda. It's exactly that thing, I hope at least. It's, where's my lambda? It's right here, okay? So I got lambda. So I've solved the problem. After somebody kindly told me that I missed a 2 somewhere. All right, so solve this. Now for the last point C is asking us, he's giving us some values, which I'm gonna copy right now. He's giving us P1 is equal to 5, P2 is equal to 2, P3 is equal to 5, and then n is 100. And then what he's basically saying is estimate the change of value in U star. So delta U star when changing from M100 to M101. Okay. And now this becomes, so there's a specific way in which the book does it, in which this compendium does it, and I think the current professor did not really go over this until now, and I hope he won't, because it involves a little bit of something that you can't really understand with what you've learned by now. But the idea is that the change of this is actually going to be lambda, okay? So it's going to be the change of this. It's just going to be du star with the change in m times lambda, okay? I don't really want to get into detail this much right here. The reason being that, first of all, I hope you never get this one, and he hasn't given any problems like this until now, so hopefully he won't. And secondly, if it comes to it, I promise I'll do a seminar and I'll explain about it. But basically, this is why. Now the reason, again, is a little bit more complicated, so we'll leave it at this. But the idea is I'm going to get 101 minus 100 times lambda. So I'm just going to get lambda times 1. So lambda equal to, and I just replace my lambda from here, from up top. Lambda is equal to 4. M is 100 minus 6p1 6 times 5 minus 2 times 5 minus 4 times 5. And no, I'm not going to compute this because I'm not really interested in the value. Okay. I would say usually just more or less memorize this for now. It has been the previous exams, but as you know, we changed professors, so I don't know if this is gonna be actually come up. And I think if you are, you might actually learn the envelope theorem by then, so it might gonna be easier. Anyway, this is for this problem. Any questions on this problem? Again, all the computation that unfortunately took me most of the time is actually pretty basic. The important steps that I did in solving this problem were writing the Lagrangian correct with a 2 here. Yeah, that's really important. Never miss a 2. So write the Lagrangian correctly, write the conditions, and then you can either have done the standard approach, which is going to take you 10, 15 minutes. I mean, should take you hopefully around that, or probably more, to be honest. Or you could have used this trick. Okay, after you've written the Lagrangian conditions correctly and you've used the trick, it's just like pure boring math. Okay, there's nothing after that. So if you have any questions on something that is not the math, I'm listening. Otherwise, I would rather not go through the math. There's no correct way of computing it. There's no required number of steps for computing math. You can do whatever you're comfortable with. I've known people that actually get more confused the more intermediate steps they have, which is fine. I've seen people do it the other way around. They need more intermediate steps. There's no correct or wrong way to do it. Okay, but I would say again that being able to compute something really fast is an extremely useful skill, and not only in the exam, but actually in whatever you do. Because everything you're gonna do if you're doing a math, I don't know, economics, solving a model, physics, chemistry, everything is based off trial and error. And if it takes you 10 years to compute something, you obviously are not gonna make too many tries, so you're not gonna succeed that many times. Make it simple, right? It's a numbers game. All right, let's do the last one, the last problem, which is from the Stumble group. But the reason I want to do it is because it shows you that sometimes the solution can be found in the strict case of the Contactor. And then comes the question, what are you going to do in that case? So yeah, let me show you how you deal with it. I don't even know which one it is. Stumble group 4, maybe? No, definitely not. Yes, it's a short one, so that helps us a lot. Okay, so problem 2. I'm just going to copy and then I'll show you what I'm writing. A firm can produce costs 1/2x². Profit P is equal to Px minus 1/2x², where x small is equal to k. Solve the profit margin using concept. Okay. Okay, cool. So this is the problem. Now, for those of you that are not doing economics, I mean, should apply to real life. The only thing firms are interested in economics, in trade, micro, whatever, is profit. Only thing is profit, okay? So all they want to do is maximize their profit. So your problem is just maximize P. So maximize the profit. Px minus 1/2x² with respect to x, with the condition x is smaller than k. So this is your problem. Now, I'm just going to do the Lagrangian, write it down, and I get Px minus 1/2x² minus lambda x minus k. Okay, take derivative with L with respect to x, and I get P minus x minus lambda is equal to 0. Very nice. And now, since this is the Contactor, this is like this, okay? Not equal. I'm writing derivative of L with respect to lambda, which would give me x minus k is equal to 0. Mistake. This is a mistake in the Contactor case, okay? Obviously, okay? So this derivative, you only write in the Lagrangian, not in the Contactor case, okay? So this mistake, I put it like this. This is a mistake, right in the Contactor. Cool. Now, the approach of solving the Contactor is just to take different cases. So I'm just writing my condition. I have the Lagrangian, I wrote the derivative. Now, the only thing I'm missing is the complementary slackness condition, which says if x smaller than k means lambda is equal to 0. If x equal to k, lambda greater or equal to 0. Okay, so I have two cases. 1, 2. Let's see what we have from these cases. First case, what was it? X is smaller than k. X is smaller than, what was it equal? Yeah, X is smaller than k, so lambda is equal to 0. This means that we have P minus X. P minus X minus lambda is equal to 0. P minus X, if this is 0, is equal to 0. So X is equal to P. That is fine, okay? Now, the second case, which is X is equal to K, and lambda is greater or equal to 0. Well, X is equal to K. So I'm kind of done, okay? So what I try to show you is that in this, the problem is extremely simple. I know you're going to tell me, but what is crucial, the crucial difference from the problem we did before is that in different cases, I got different solutions, okay? These two are actually both solutions. Now, what would you do when you get this in an exam and you're asked, you're asked to solve the problem and you get two solutions? What you do is just plug these two in and see which one is bigger, okay? I got two candidate solutions. So at this point, the Contactor cases gave me two candidate solutions. How to check which one is the good one? How to check which one is the good one is replace in the function I'm maximizing in the max function and see which one is bigger. Okay, this is what you have to do. In my case, given the fact that I don't really know the relationship between K and P, it's even if I replace it in, I couldn't form a hypothesis. Okay, if I just replace in, for example, I'd have P, a product of P is equal to P squared minus half P squared, which is equal to half P squared. And then product of K, P of K would just be PK minus a half K squared. So it would just be half K P minus K. Which one is bigger? I have no idea. Okay, I can't tell. So for now, they're both candidate solutions. If they gave me numbers here, if they told me P is 4, K is 1. I don't know. I could tell you which one is bigger, and I could tell you which one is the solution. Okay? I could just tell you if I replace here, I can tell you that, for example, this one is bigger. If this is K minus 2. 1 second, please. Sorry. Alô? 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 Eu posso sonar posso sonar os ativos lá dentro. Eu sou aqui para ver o Jan. Sorry for that. Okay. Yeah, it's K minus speed. This map is horrible. Where are people at? Just tell me I'm wrong. Okay. What I meant is we're just going to factor out a K and I'm going to get P minus half a K. This is what I meant. Okay. And yeah, if you plug in the values and etc., then I could tell you which one is bigger. In this case, I can't. But again, main idea is if you get two solutions in the two different cases, you need to plug them in and see which one is bigger and see which one is the actual true solution. Okay? Any questions on this approach? Obviously, yes.
When you show calculus,
Mm-hmm.
that one like they were still different values. So like x equal to 2, 1 is less.
That is in point B. Yes.
Oh, okay. Okay.
Yeah. I know exactly what you're talking about, and that is in point B. One thing, I guess, here in which we're gonna go right now to point B, but one thing in which you can relate what you're saying is, in this case, X is smaller than K, X is equal to P. So this is the case for P smaller than K. But this is just a follow-up of applying the conductor. It's not how I made the cases. We're gonna see in point B that in point B, which asks me to solve it without using the conductor, I'm gonna employ these cases, and I'm gonna show you in a second. Okay, and here X is small is equal to K. I would assume it's the other one, which is K is greater than P. But again, these I don't want to write these here because these are like follow-ups of this. They are not the way I spread my cases here. Okay. For the second point asks me, point 2 asks me solve without conductor. Can I solve it without conductor? Can I get the same solutions without conductor? And I said, yeah, I have my P, which is just XP minus 1/2 X squared. Yeah, okay. And I take derivative of P with respect to X. I'm just not using a Lagrangian, I'm just using critical points here, okay? I don't care about anything. So I take derivative and I get P minus X, okay? Now, you could say, I want this to be equal to 0, and I would be done automatically. Okay, so it means X is equal to P. And here we look at the cases, okay? Here's where I look at the cases. Because X has to be in 0K. X is smaller or equal to K. What if case 1, price is gonna be greater than K? If the price is greater than K, can X be equal to price and still have satisfied? So my question is, can X be equal to price and P and X still smaller or equal to K? That is my question right now. Think about it. So can X be equal to P? So this would mean that P is smaller or equal to K. but I took the case where P is greater than K. So obviously this is a contradiction. Contradiction. Which means X cannot be equal to P, okay? Why? Because X is in this interval. X is smaller or equal to K, so it's between 0 and K, okay? I cannot have X be equal to something outside this interval. If X is from 0 to 200, I can't say X is equal to 400, okay? It has to be inside the interval. So how do we solve this? Well, my claim is that if P is greater than K, my claim is that P of X is greater than 0 for all X greater or equal to K, which is smaller than P from here. Everyone follow the logic? So again, I am studying the case where P is greater than K. If I'm in this case, I cannot have X is equal to P because I know that X has to be smaller than K. So it would look something like this. The equation would look P is equal to X, which is smaller than K, but P is greater than K. So I would have K is strictly greater than K, which is false. Okay, so X cannot be equal to P. So now I just look at the function and I see the fact that if P is greater than K, then P is greater than X for all X's smaller than K. Okay, that is the argument. Makes sense? Well, if I replace here, I just get P is greater than X. P greater than X. Okay, so it's true. So what does this mean? If the first derivative of a function is greater than 0, it means that the function is increasing in X. Okay, strictly increasing. If it is strictly increasing, it means I'm going to find my maximum for P at the edges. So it means that if my profit is increasing with X, I want to sell and produce the maximum amount. I want to maximize X. And because X is in 0K in this interval, it means, and I want to maximize X, it means X is equal to K. Okay? And this is one of the previous cases that we got. So again, I had this X is equal to P, and I just had to pay it. I had this X is equal to P, and I just had to pay attention that X is in 0K. Okay? Maybe, as you've seen in, I guess, some of the exercises, the critical points are outside of your interval. That is the problem in this case. If P is greater than K, then the maximum of this function is attained outside the interval. And I can't give X that value because it's outside my interval definition, my domain, however you want to call it. So I noticed that X cannot be equal to P. But I also saw that if P is greater than K, then P minus X is greater than 0. So it is an increasing function in X. So me maximizing this, which is not the global maximum of the function, but it's just the maximum value within my interval of 0K, I'll just take the maximum X I have in this interval, which is going to be K. That is the logic that should come up. Okay, any questions on this? Too many to count? Okay, and now the second case, which is much easier, is P is smaller or equal to K, which means that P is inside the interval 0K, and I said that X is equal to P, and this is okay. It's okay. It's a good solution. It's from here, right? X is equal to P is a valid solution, is okay, because P is smaller or equal to K, so P is in the domain or the interval of definition. Okay, any questions on this? Any questions on the two cases? Does this answer your question right now, how we did it, I think? Yeah, this is, so when I use the contactor conditions, the contactor already kind of gave me these cases, so I didn't need to worry about it. But now, since I solved it without using the contactor, I had to take these cases by myself. I had to consider them by myself. That's why I split it like that. And so my two solutions are X is equal to P and X is equal to K, which are the two solutions that I got here. Okay. But here I got them with the contactor condition. Here I got them by hand. Okay, and point C is really easy as far as I remember. Asks us, what would the solution be if X is equal to K? First of all, so I think I know what the professor aimed to do with this question, but I think you're gonna get way more by looking outside of the box, because sometimes I've seen a lot of problems, even with some of the assignments we got, is what is the point of solving this problem if he's telling you X is equal to K? I am maximizing P of X over X, but I know X is equal to K. So my question is like, what is there left for me to do? They're asking me to find X when I know X is equal to K. I don't understand. So I'd much rather appreciate the idea if you guys can just sometimes zoom out of the problem, okay, and just see what the problem is asking you to solve. Like in this case, it's asking me to maximize over a variable when I know X is equal to K. So the answer to this problem is, what would be the solution if X is equal to K? It would just be X is equal to K, question mark? It doesn't make sense, right? But the same logic, this might seem trivial and stupid and whatever, but the same logic that I applied here, which is like bare bone, right? Like I just noticed that the variable, a variable which I'm asked to maximize over, is actually now a constant. So there's no point in doing the maximization over it to start with. The same logic applies to your mandatory assignment in point C at this point. It's exactly the same logic. If a variable is given to be equal to a constant, is there any point even maximizing over it anymore? Of course not. It's a constant. It's not going to affect anything. I can write all the derivatives and everything right now. I won't change the value of this. It's still going to be X equal to K, right? So what's the point of me doing any more computation? None. So if I were to answer this question, well, would you get the same optimal solution if you replace the constraint with X equal K? Would you, which would allow you to use a simple Lagrangian method? I would, if I was on the exam, and I think I actually did this, of course not on this one, but I did this on some bigger exam. I just wrote C question mark, solve what? X is equal to K, question mark. And then if you wanted me to give the answer, not going to find X is equal to P, which was the other solution right here. Okay. But this would, if I was grading it, this would give full credit for me. Because It seems, and again, it seems really basic, but you can mask this simple event, which is transforming a variable into a constant with equal. And it can get really hard. Like, look, again, mandatory assignment, part C is exactly what this is. When they tell you x1 is equal to 1. And the same logic applies. If a variable becomes a constant, why even maximize over it? Why just not completely drop it out? But I guess that's time up for us. So that would be all for today. And if you have any questions, just let me know. I will publish this note in the same folder. I don't know if you're using them, but it's one click for me. So yeah, have a great day, everyone.